All right, hello everybody. This is the video I promised you introducing the concept of induction. Okay, so the term induction is used in a lot of different ways, and according to the dictionary on my iPhone, I use WordWeb, the definition that's going to be relevant for our conversation is actually the third one listed in WordWeb, which states that induction is reasoning from detailed facts to general principles. In other words, we go from a very specific case to a general idea or a general set of cases. And that's what mathematical induction is actually all about. So mathematical induction is a proof technique that involves several steps. So we begin with something we call the induction hypothesis. So this is the thing that we're hoping to prove using induction. Okay, so for example, we may want to prove the statement that for all positive integers n, 1 plus 2 plus 3, etc., all the way up through n is equal to n times the quantity n plus 1, all divided by 2. Okay, so that's what we're wanting to prove for all positive integers n. We'll begin by identifying what's known as an induction base, or sometimes we'll just call it a base case. And this is a specific example that we can show to be true. Right? So for example, we might choose n equal to 1, and we plug that into our hypothesis, and we get 1 is equal to 1 times the quantity 1 plus 1, all divided by 2, which of course, we do the arithmetic and we can see that that comes to 1. So 1 does indeed equal 1, and we're in a good place. So we've shown that that this equality we stated initially is true in the case of n equals 1. Now what we want to do is show that if, okay, so our inductive step is to show that if it's true for n, then it's also true for n plus 1. So we get to assume that it's true for n, and indeed we found a value for n for which it is true. And then what we want to do is use arithmetic essentially to show that it must be true for n plus 1. So what we'll do is we'll restate the hypothesis, okay? So for our induction step, if I can speak correctly, for our induction step, we will restate the hypothesis, but we will replace n with n plus 1, okay? So now we're saying 1 plus 2, etc., all the way up through n plus 1 is equal to n plus 1 times the quantity n plus 1, all divided by 2. All right, so let's try to work through this example on the next page. So I'll go ahead and rewrite it here real quick. And we'll begin by trying to kind of expand the left side, okay? So if this is 1 plus 2 plus so on and so forth all the way up through n plus 1, then it must also include n in that sum, right? So all I've done is kind of expand this out a little bit. The reason that's useful is because now I can identify something that I can condense, okay, and make look somewhat more like the thing on the right side. In particular, I can use our induction hypothesis, which states that this quantity can be expressed in this way, right? We said 1 plus 2 plus 3, so forth, all the way up through n is equal to n times n plus 1 over 2. So I can plug that in place of that sum, right? So I now have n times n plus 1 over 2 plus the quantity n plus 1. We'll go ahead and multiply that second term by 2 so we can put everything over a common denominator. And then we'll just go ahead and do a little bit of multiplication, right? So I'll multiply the n times the n plus 1 term and the 2 times the n plus 1 term, and I end up with n squared plus n plus 2n plus 2 all over 2. Now, of course, we can combine the n and 2n terms into 3n, so we have n squared plus 3n plus 2 all over 2. And factoring that, we get n plus 1 times n plus 2 all over 2. Now, it doesn't quite look like we're there, but hopefully you're beginning to see that this is pretty close to what we wanted to end up with. We wanted to show that the left side is equal to the right side, and the right side is n plus 1 times the quantity n plus 1 all over 2. Well, if we expand our 2 into 1 plus 1, then we end up right here, which is exactly what we needed. So let's recap what we've done here. What we just completed is our induction step, in which we showed that if our hypothesis is true for n, then it's also true in the case of n plus 1. And if we combine that with our induction base case, wherein we plugged in a 1 for an n value, then we've now shown that that this statement is true for all values of n that are greater than or equal to 1, which is going to be all positive integers. Okay, so we are done with this particular proof. That's really all there is to induction, is those steps. Now, the tricky part comes in the arithmetic, right? In the algebra, in figuring out how to get the two sides of our equation to match. And so practice makes perfect, so we're going to practice. So let's look at another example. We want to show for all positive integers n that 1 squared plus 2 squared and so forth all the way up through n squared is equal to n times n plus 1 times 2n plus 1 all over 6. Okay? Now, to begin with, it's your turn. This is where I want you to pause the video and see if you can use induction to prove this statement. All right? And give it a go. If you get it, great. If you get stuck and you're not able to make progress for a while, then in neither of those two cases, come on back, unpause the video, and I'll show you a way to solve it. I say a way because you may have used a little bit different process to get to the same solution, and that's completely fine. So go ahead and pause the video, and I'll talk to you when you get back. All right, welcome back. So let's go ahead and do this problem. I've rewritten our hypothesis here. Again, it's 1 squared plus 2 squared, etc., all the way up through n squared is equal to n times n plus 1 times 2n plus 1 all over 6. Okay, so our base case here, or a good base case to use, is n equal to 1 again. So we plug that in. So 1 has been inserted for all cases of n here, and we do a little bit of simplification, and we end up with 2 times 3 over 6, which of course is 1. 1 equals 1, so 1 squared, which is 1 of course, is equal to all of this other stuff, which brought us to 1, and so we have established that this is true in the case of n equals 1. Okay, so now we go on to the induction step. So as we explained before, we'll simply plug in n plus 1 wherever we saw n. So we now have 1 squared plus 2 squared, etc., all the way up through n plus 1 squared is equal to all that stuff on the right. I'm not going to bother reading it. You can see it. As is our normal habit, what we'll do is expand this term on the left here a little bit, trying to get it into a state where we can do some replacing, right? Where we can use our hypothesis to kind of simplify things a little bit. So sure enough, if we expand this out, we can see that 1 squared plus 2 squared, etc., up through n squared must be present in that sum. And so if we show that, we can grab that piece of the sum, and using our induction hypothesis, we can replace that with this expression here. And so we end up with n times n plus 1 times 2n plus 1 all over 6 plus n plus 1 squared. Okay, now where to go from there? Well, to begin with, it seems like, again, it would make sense to get everything all over a common denominator. So we'll multiply the second term by 6. That gets us here. Then I notice that in both of these terms, we've got this n plus 1 expression. And so I think it's a good idea to factor this out. And that's for two reasons. I note that in the expression I'm trying to get to, there is an n plus 1 term. And I also note that in the expression I'm trying to get to, there are no squared terms. And so factoring out that n plus 1 gets rid of the square and gives me one of the terms that I'm going to need in the final solution. So I think it's a smart thing to do. Okay, so next I'm going to go ahead and I distribute the n and 6 terms that I've got for those two expressions inside of the square brackets. So my 2n plus 1 times n gives me 2n squared plus n, and the 6 times n plus 1 gives me 6n plus 6. Now what to do? Well, once again, I've got a squared term sitting there. So I think I'm going to want, well, before that, pardon me, we'll go ahead and combine that n plus 6n into 7n. And then what I want to do again is I'm looking at this expression and I'm not really liking that n squared. So I think I need to factor this to get rid of that. I notice that I've got this 2n squared, so that tells me that in the final set of terms I'm going to be working with, I'm going to need a 2n in there, and then I'll multiply it by another term with an n. All right. Then I note that I've got a 6. I'm adding a 6. So, factors that would contribute to giving me a 6. If I've got a 2 times a 3, that would give me a 6. So I'm pretty sure I'm going to have a 2 and 3 involved here. And somehow I've got to sum up terms that have n's up to 7n. Okay, so I look at that and I see that, well, if I multiply 2 by 2n, I'll end up with 4n. And then if I was to multiply 3 by n, I would end up with 3n, and so that would give me a total of 7n. So putting the 2 over here, so it gets multiplied by the 2, and the 3 here, so it gets multiplied by that single n on the other side, gets me what I want. Okay, so moving on, we can now rewrite the top as n plus 1 times n plus 2 times 2n plus 3 all over 6. Okay, now it's probably good to again review where we're trying to go, and that's this expression here. And I note that I'm kind of heading the right direction. I've got this n plus 1 term, and looking at n plus 2, I'm pretty sure I can turn that into n plus 1 plus 1. But I've still got something weird going on here with this 2n plus 3. I've got to turn that into a 2 times n plus 1 plus 1. Okay, so again, I've identified those first two are looking good, and I just want to work on this guy right here for the moment. So what I think I'll do is break that 3 into 2 plus 1. I'm doing that because that gives me that plus 1 that I need at the end, and then I note that I can factor that 2 out from the 2n plus 2. So I've got 2 times n plus 1, and voila, that is exactly what I was looking for that part of the expression. So I can now rewrite this. Note that I've got the n plus 1 term, I've got the n plus 1 plus 1 term, and finally the 2 times n plus 1 plus 1, so all over 6, so we are golden. That completes the induction proof. All right, let's look at kind of a fancier way of approaching some of these. So in this case, we want to show that for all non-negative integers n, and note that when we say non-negative, that's going to include it's going to include 0. We want to show that 2 to the 0 plus 2 to the first plus 2 to the second, etc., all the way up through 2 to the n is equal to 2 to the n plus 1 minus 1. Okay, now some of you might recognize this as being a common equation that we use when we're dealing with binary, right, with sets of bits. So we're going to actually prove that this is true. So another way of writing all of that stuff I've got on the left is to use the summation symbol and change our notation a bit. So now what we're saying is that the sum of 2 to the I from I equals 0 up through n is equal to 2 to the n plus 1 minus 1. Okay, so hopefully you've seen this notation by now, and hopefully you're fairly comfortable with it. If not, you're going to be because you're going to see it quite a bit. All right, so we want to show that all of that is equal to 2n plus 1 minus 1. Okay, so that's our hypothesis. For our base case, we're going to choose n equals 0. So we'll plug that in. We get 2 to the 0 is equal to 2 to the first power minus 1. And of course, 2 to the 0th of anything anything to the 0th power is 1. And that is equal to 2 minus 1, which indeed is 1, so we're in good shape. Okay, so we've shown that our hypothesis is true for some value of n. Now let's try to do the induction step, which involves showing that if it's true for n, then it's also true for n plus 1. So once again, we simply replace all of our n's with n plus 1 and try to make the two sides equal to each other. Clearly equal to each other, I should say. So what we're going to do is we'll start with this expression on the left. And Same strategy we've used before. We're going to look to see if we can use our hypothesis to simplify any of this. And sure enough, if we expand out that summation statement, then we can say that 2 to the I, the sum of 2 to the I from I equals 0 to n plus 2 to the n plus 1, that is equivalent to the expression 2 to the I from I equals 0 up through n plus 1, or rather the summation of 2 to the I from I equals 0 to n plus 1. All right, so we can use our hypothesis to replace this term with 2 to the n plus 1 minus 1, and then the last little bit there, plus 2 to the n plus 1. We now have two identical terms here, and so we can express them both using multiplication instead of addition. So 2 times 2 to the n plus 1. And of course, anything raised to a power multiplied by that same thing becomes that thing raised to the power plus 1, right? If this was 2 to the third times 2, it becomes 2 to the fourth. So we can rewrite this now as 2 to the n plus 1 minus 1, which is exactly what we needed. And so our induction step is complete and the proof is finished. All right. Now, I'm going to, at this point, give you another example and ask you to work through it. So I'd like you to show that for all non-negative integers n and real numbers r not equal to 1, we want to show that the sum of r to the I from I equals 0 to n is equal to r to the n plus 1 minus 1 over r minus 1. And you might note the previous example, r was 2. So we want to show that this is true in general for all real numbers where r is not equal to 1. Okay, so go ahead and work this problem. I am not going to present the solution in this video. Instead, what we'll do is we'll use this as our warm-up at the beginning of class on Monday. All right, so have at it, see how well you can do on this, and at the beginning of class, we'll discuss the solution. We'll see you soon. Thanks.